This lecture is specific to Conceptual Physics AB. We take a look at one example involving the one-dimensional elastic collision. In an elastic collision, we assume that the heat loss is negligible. This then means that the total kinetic energy of the system is a conserved quantity, as well as the momentum being conserved. The situation that we'll look at is one of the strategies that you need to win while playing pocket billiards or pool. As long as you don't spin the cue ball when you strike it with the cue, only two things can happen, one of which is going to be examined here in the one-dimensional elastic collision situation. I've phrased this for us as a problem. After I've done the problem, then I will go ahead and demonstrate it here by using my carts. We'll picture the carts here as pool balls. Okay, let's take a look at the example, copy it down as I proceed. Two billiard balls of equal mass undergo a one-dimensional elastic collision. The cue ball has an initial speed of 1 meter per second, and the target ball is initially at rest. Find the final speed of each ball. This is the first strategy that you need in order to win while playing pocket billiards. Okay, now let's set up the situation in the following way. Okay, so right here we'll say is the cue ball. It has a mass m. Right here is its initial velocity in this direction. The magnitude is given to us as 1 meter per second. Okay, right here is the target ball. It also has the same mass m. This object is initially at rest. V2 naught is equal to 0. And then in the elastic collision, the objects bounce off of each other. This then means that the two objects will each have a final velocity and they're different from one another. So then therefore, after the collision occurs, the cue ball is going to have some final velocity, call it m as its mass, and v1 final as that final velocity. And then we have the second object, the target ball, also of mass m. It then has a final velocity, which we'll refer to here as v2 final. So because we have two unknowns in this problem, v1 final and v2 final, this means that algebraically we're going to need two equations. So here is the first of those expressions. Let's go ahead and set up conservation of momentum. So, change in momentum of the cue ball plus the change in momentum of the target ball is equal to 0. And now in this problem, let's start going ahead and filling in our terms of mass times velocity for the momentum vectors. Okay, so first of all, the change in momentum of the cue ball. So its final momentum after the collision is m times v1 final. And then minus the initial before the collision, which is m times v1 naught. Okay, and then we have our second object here, the change in momentum of the second object. Its final momentum first is going to be m times v2 final. And then minus the initial, which is 0 because the object begins at rest. Like so. And now let's go ahead and simplify this expression. First of all, the masses are the same, so then therefore they cancel from the expression. So let's go ahead and get rid of that, like so. And then right here, let's go ahead and plug in the initial velocity of the cue ball. Remember that that was given to us as 1 meter per second. So now what I have is this, v1 final plus v2 final, and then minus 1 equals 0, like so. And then this right here is the first of what will ultimately be two equations and two unknowns. I'll take you through the algebraic procedure of how we then solve for those unknowns in just a few minutes. But before I do, I need to get my second equation. The second equation is the elastic approximation. We're assuming that the heat loss that occurs during the collision is negligible, so then therefore the kinetic energy is a conserved quantity. Here's then how we write that. So this is known as the elastic approximation. The change in kinetic energy of the cue ball plus the change in the kinetic energy of the target ball is equal to 0. Now in reality, it's not equal to 0. In reality, there is a little bit of energy lost as heat, but we're considering once again the heat loss to be negligible. So this expression is an approximation. As we'll see when I demonstrate this in a few minutes, it's a reasonable approximation to make in this problem. Okay, now let's go ahead and start filling in the terms for the change in kinetic energies of each object. So first of all, for the cue ball, it's going to have a final kinetic energy after the collision. We'll write that as 1/2 m times v1 final squared. And and then minus its initial kinetic energy before the collision. That's 1/2 m v1 naught squared. Okay, then we have the change in the kinetic energy of the second object, the target ball. It's going to have a final kinetic energy after the collision, 1/2 m v2 final squared, and then minus its initial kinetic energy, which is 0, because the target ball begins at rest. And then this is all equal to 0 on the right-hand side of the expression. Okay, let's simplify this equation. When we do, immediately two things cancel out from each term, the 1/2s and the m's. So let's go ahead and get rid of those. So the 1/2 cancels out, and the m cancels out. And then here's what I have left. I'll write it down here. I have, first of all, v1 final squared plus v2 final squared. And then right here, minus 1 squared. So minus 1 is equal to 0. And that second expression now is the second of two equations and two unknowns. Depending upon your level of mathematics, you might be able to very easily solve the remainder of this example. However, let me take you through the remainder of the math here slowly, especially for those of you that are not quite familiar with how you solve a system of two equations and two unknowns. You'll learn the rudiments of how we do that here. Okay, I'm going to do some erasing here to give myself some room. Let's get rid of all the stuff that we don't need. So, and now here's how we go about doing the algebra. What I'm going to do is take the top expression, this is the momentum equation, and I'm going to solve it first for V1 final. So over here, let's solve for V1 final by taking these two terms and moving them to the other side of the expression. That gives me this, like so. And now what I do is I take that expression for V1 final that I just found, and I plug it into here. And when I do, I have to square it, so then therefore we're going to use a process called foiling when we square. Foiling is an acronym that stands for first, outer, inner, last. It's a specific way in which we multiply terms together. Once again, you'll see this extensively in your algebra class, perhaps a little bit later on. However, doing the process is quite straightforward. Here's what I mean. So I'm going to take this negative V2 final plus 1 and plug it here and square it. So that means that I have to multiply it by itself. This is where the foiling process, as it's called, will come into play. Then I have right here plus V2 final squared, and then minus 1. Like so. Okay, now let's erase the stuff I don't need. I don't need these guys anymore. I can do the remainder of the algebra with what I have here. And now here's this foiling process. Here's how you multiply these terms together. You first of all do this term here multiplied by this term. So negative V2 final times negative V2 final is positive V2 final squared. And then the next term in the foiling process is to do this negative V2 final times 1. The next term is this 1 times negative V2 final. And then the last term is 1 times 1, like so. And then I still have these remaining terms. Okay, this foiling process, as I just did, you'll learn extensively in algebra class if you haven't seen it already. Okay, now the equation that I end up with here looks a little bit messy, but it does simplify for us rather nicely. First of all, notice that the positive 1 here cancels out with the negative 1 here, like so. So let's go ahead and get rid of that. And now let's add the terms that remain. Right here is a V2 final squared. Right here is the V2 final squared, so I have two of them. And then right here is a negative V2 final and another negative V2 final, so I have two of them. Like so. And now let's go ahead and solve for the only unknown which is left, and that's V2 final. Once I have the value of V2 final, then from there we can go ahead and figure out what V1 final is by going back up to this step here. Okay, now to solve for the V2 final, what I'm going to do is take this term and move it to the other side first. Like so. And then when I get to here, a number of things cancel out. Okay, first of all, the 2's cancel like so. And then I could also cancel a V2 final here and here like so. And then here's what's left. V2 final is equal to, what is this? It's not 0, it's 1. It's 1 meter per second. So the final velocity of the target ball, 1 meter per second, is the same thing as the initial velocity of the cue ball, 1 meter per second. And now that I have this value for V2 final, then the last step is just to jump back up to here, plug in the V2 final that we just found, and calculate the V1 final. So let me go ahead and do that. Let me clean up the board, however, prior to doing so. There we go, and that now gives us the following. So V1 final is equal to, first of all, negative V2 final, so negative 1 plus 1 is equal to 0 meters per second. So the cue ball ends up at rest. Notice that the objects just exchange velocities. Here's then what occurs. Right here is the cue ball, initially moving that direction at 1 meter per second. Right here's the target ball, initially at rest. And now watch this. The cue ball ends up at rest, and the target ball ends up with that speed in that direction of 1 meter per second. The objects just exchange velocities. This is the only thing that can happen as long as you strike the cue ball head on with the target ball. As long as you don't spin the cue ball, the only thing that can happen is that the cue ball ends up at rest and the target ball ends up with the same speed that the cue ball initially had. This problem is actually a specific case of a more general example of what happens when you take two objects of equal mass and collide them in some manner. When you do, they always exchange velocities as long as the masses are equal. That's what we see here in this problem. So in this problem, the target is at rest initially. This is initially at 1 meter per second. This ends up at rest, and this ends up at 1 meter per second. Once again, this is the first strategy that you need to win while playing pocket billiards.